We'll see how these floating point numbers can be represented using computer, right? Computers means what? There are various architectures, right? There are various vendors design these architectures. So some of them are Intel, and we have ARM processors, right? We have AMD processors, we have Celeron processor, MIPS. There are a lot of people who create this architectures, otherwise who design processors. Now the question is how they understand, that means how they interpret the floating point numbers is a question. When you write a pattern, then how they interpret, correct? For that there should be a common agreement. What happens is, example, let's say Intel understands your representations in one way, then other processors like ARM understands in a different way, AMD understands it in a different way, then it creates chaos, right? So to avoid that, it creates ambiguity. To avoid that, there should be a common agreement. That means there should be an agreement between all these processor designers and users and everyone and entire world. That's why that common agreement from now onwards is, according to the standard IEEE 754 standard especially, is like this. So your floating point numbers are actually 32-bit numbers. That means that will be in your processor. Example, you are using a computer, then when you write a floating point number, then that will be represented using 32 bits. Okay. So you will be given 32 bits, we have to write a pattern, then that pattern will be understood based on this model. So one component is sine, second component is exponent, third component is mantissa. Already now you are comfortable with what is sine bit, exponent bit and mantissa bit. That's why I explained you first, how human beings write the floating point numbers. Now we are coming to computers and the standard, right? Now in the GATE exam, they will ask, if they ask any question, if they mention IEEE 754, you have to follow this one. In IEEE 754 also there are two representations. One is 32-bit representation. There is another model, that is, this is single precision. Okay, single precision. So there is other version, that is double precision. That is also we are going to study. If you understand the single precision, you can understand double precision, not a big deal. Now sine is 1 bit. We write here 0 or 1. 0 means positive number, 1 means negative number. That's it, close. Now remaining in out of 32, the next 8 bits are going to represent signed exponent. How to represent that signed exponent is, generally for that we use XS 127 representation. Don't worry, whatever the pattern you write, that is interpreted as XS 127. I mean, we write in XS 127 representation. Now how to convert it into decimal, I will tell you. Okay, so just remember it. That means your exponent is XS 127. Okay, and it's a 8-bit pattern. Now the remaining bits, if you see, 1 bit is gone, 8 bits are gone. 1 plus 8, 9. Remaining 23 bits are mantissa, and mantissa is represented as a 23-bit fraction. Sir, what is the meaning of fraction? I will tell you. So whenever you write 2-bit number like this, if I say this is a fraction, that means this binary pattern is represented as a fraction, then the value of that is, it is like having point here like this. Okay, so if you have 0.11 in binary representations, already I told you, what does it mean? It will be like this. The weightage of that first bit is 1 by 2, this will be 1 by 4, correct? So then 1 by 2 plus 1 by 4, it will be 1 by 2 means 0.5 and 1 by 4 means 0.25. It will be 0.75. In decimal, the meaning of this one is 0.75. Okay, so that is the meaning of this fraction. Okay, now we'll see one more fraction and we try to understand. If I write 0, 0, 1 followed by all zeros, then what is the meaning of this one? What is the value in decimal? If you want to know, then you just give weightages like this: 1 by 2, 1 by 4, 1 by 8, 1 by 16, so on. Since it is fraction, then there is an implicit point here. Okay, that's why it would be 1 by 2, 0.5 plus 1 by 4, 0.25 plus 1 by 8. I'm sorry, because the weightage is 0, right? 0 into 0.5, 0, plus 0 into 2.25 is 0. Only we have this bit, 1 into 1 by 8. It would be, I think, 0.125. So this is the meaning of this binary pattern if it is represented as fraction. That's it. Now you understood this one. You understood exponent, of course, not clearly. I will explain what is the meaning of this XS 127 representation. Once this pattern is written, then what is going to happen is this pattern will be represented overall like this. minus 1 whole power s into mantissa, but 1 point mantissa. Okay, whatever the mantissa you get here, that will be interpreted as 1 point mantissa. I will tell you the reason why not 0 point mantissa. We have studied that 0 point mantissas, right? But here it is actually 1 point mantissa. We'll see the reason slowly. Let's blindly follow first. Into base power exponent. So base power, here exponent is written in this way. So actual exponent is, let's say if it is, this is e minus 127. Okay, blindly remember it. So e minus 127. Okay, so this is the way it will be represented. Okay, now, so here why this one 1 point m and why it is e minus 127 and what is the base I should address. Let me address what is base. So here, because it's binary numbers, then base is 2. That is again implicit. Okay, it's a common understanding from now onwards for this IEEE 754 floating point representations. So base is 2. Now I should tell you what is the, why this 1 point model, why not 0 point model, that is one thing. So this is called normalization. Okay, writing 1 point m means normalization. I will tell you what is normalization, because don't try to understand everything at a time. Slowly you can understand, not a problem. Okay, now what we do is, first of all, forget about the reasons, but we try to understand. We take one example and we will see what is the meaning of, what is the value of that number if I represent it in using this pattern. Okay, example you see here, 0 0 0 1 0 1 0 0 0 0 0 1 0 1 0. If I write followed by all zeros. Okay, if it is given sign here, exponent here, mantissa, what is the decimal value of this pattern? This kind of question they ask in GATE exam. Then we will see. See here, minus 1 whole power s. So what is sign bit? 0. Blindly write it into 1 point mantissa. What is the mantissa value? Here like this, 1 point. Blindly copy first. 0 0 1 0 1 0, so on, some zeros. Okay, into base 2 power exponent minus 127. E minus 127 means, since it is excess 127 representation, then if you want to know the exact value, we should subtract 127 from E. Okay, first of all, blindly subtract. Take E, binary value of E. So E here 0 0 1 0 1 0 0 0. In unsigned numbers, what is the value of 0 0 1 0 1 0 0 0? Tell me. In unsigned numbers, it is 240 241 2 square 2 cube 244 245. It is 32. This is 8, correct? So 32 plus 8, 40. In excess 127 representation, when you write 40, that is treated as 40 minus 127. Okay, so that's fine. So the binary 40 is equivalent to 40 minus 127 in excess 127 representation. That's why. So 40 minus 127 is how much? 87, right? Minus 87. That is the reason finally it become minus 87. Let us write 2 power minus 87. Right. Now, sir, what is this 1.001010? If you want to convert it into decimal, because you have converted this entire thing into decimal, right? If you want to know the answer in entirely decimal, then we convert this also. So this is now mantissa in fractional representation. You know the idea, right? So what is the bit, this bit's weightage? 1 by 2, 1 by 4, 1 by 8, 1 by 16, so on. Okay, let us simplify. 1 by 2 into 0, 0, 1 by 4 into, and what about this 1? Whenever I write 1 here, it will be in binary. Let's interpret this as fractional representation. Did you remember? Already I explained you fractional representation. In fractional representation, so the value of this one is like this. The weightage of this one is 2 to the power of 0. 2 to the power of 0 means 1. 1 into 1, 1, plus 1 by 2 into 0, 0, plus 1 by 4 into 0, 0, plus 1 by 8 into 1. What is that 1 by 8 into 1? 0.125. Better, let me keep 1 by 8 as it is. I will tell you. Plus 1 by 16 into 0, 0, plus 1 by 32 into 1, 1 by 32. So remaining all are zeros. Then if I simplify it, 1 plus 1 by 8 plus 1 by 32 is nothing but, so 32 is LCM, 1 by 1, 1 into 32, 32. You know the simplification, right? 8 4s are plus 32 1s are. So you get 37 by 32, right? 37 by 32. You simplify it, whatever you get. So minus 1 whole power 0 is plus 1, correct? Now 37 by 32, if you simplify, it would be something like 32 1s are 32, 5, 50, 32 1s are 32, 18, 32 5s are 1.15 something you get, into 2 to the power of minus 87 is the final answer. So finally this binary patterns meaning is 1.15 into 2 to the power of minus 87. See, very small number, right? It is almost 0, correct? So that's why I can say that. So using these floating point numbers, we can represent very, very small numbers, correct? Similarly, we can represent very large numbers, right? Now we'll continue the discussion. So I would like to answer two questions here. One is why exponent is in excess 127 representation. Before that, first you should understand one thing. This exponent should support negative numbers also. That means your exponent should be a signed number. Yes or no? Sir, why signed number? Why not unsigned? If it is unsigned, then only positive numbers we can represent. Then if you cannot represent negative number, then smallest numbers we cannot represent. Recall. So here minus 1 whole power, example you see, minus 1 whole power 0. Assume that let's say we are representing positive number. Then here 1.m is going to at most give something like 1.25 or 1.5 something, right? So you can't have definitely the number will be between 1 to 2, right? You can have 1.25, otherwise 1.5. So in this pattern we will be getting some number like this into base power exponent, right? So you tell me, if I want to really represent smallest number, that means I want very small number, then this exponent is going to play a role, correct? If this exponent is 10, then it will be 1.25 into 2 power 10, right? If I want to reduce the number, then I can use 9 here, further 8, further, in that way I can come up to 0. If you are only representing unsigned numbers, then what is the number you can represent at most smallest in the positives? Minus 1 whole power 0 into, that means positive, into 1.25 into 2 power 0, that means after all 1.25. I want to represent further small, okay? For that I can use here 2 to the power of minus 1, try to understand. If somehow if exponent is representing minus 1, then this will become 1.25 into 2 power minus 1, which is 1 by 2, then 1.25 by 2, 0.625. So slowly you will realize that if I take here 2 power minus 20, let's say, then this is equivalent to value wise 1.25 by 2 power 20. That is what the meaning of IEEE 754 representation. So that's why it would be 1.25 by 2 power 20. Very large number in the denominator. So overall value will be very small. So finally you realize that if exponent is negative number, then you are going to represent smaller number, correct? That's right. So you should be able to represent negative numbers also. Now recall, generally how to represent negative integers? We have ones complement representation, signed magnitude representation, we have two's complement representation already, right? So one of them we can pick. But sir, why exponent is in excess 127? So I will tell you the reason after some point of time, not immediately, because you can't understand and it is not required now. So but remember one thing, we use excess 127 to represent positive and negative. Example, when you write exponent 0, then because of excess 127 representation, the decimal value of that is minus 127. Sir, if I write binary pattern such a way that it is 1, then that is going to represent what? 1 minus 127. That's why in the formula we have minus 127. So why we have e minus 127? Since this representation is excess 127, we have to remove 127. 1 minus 127 minus 126. 2 minus 127 minus 125. So in that way, what is the highest number we can represent using 8 bits? So using 8 bits, the maximum binary pattern we can write 8 ones, right? Now, so in what is the unsigned value of this one? So unsigned value will be 255 with 8 bits, remember it, okay? So just check it out otherwise. So we will be having 255, but 255 will be, because of excess 127 notation, 255's meaning is 255 minus 127, that means 128. Though you write 255 here, that is actually 128. Whenever you write 0 here, that's actual value is minus 127. That is the way, so we will be understanding. Now remember one thing, whenever really you want to have a power of, example, you want to represent a number called 2 to the power of minus 126, then in the exponent we have to write 1. That is the way we have to plan it out. Okay, so this is about x is 127. Still I did not tell you why x is 127. Why not 2's complement? You can use 2's complement also, right? Using 2's complement also, using 8 bits, we can represent these numbers. So I will be teaching you that later, little bit later, because I will tell you one line at this moment. After that I will elaborate it. So why we use x is 127? Because in x is 127, if you represent the patterns, then imagine, what if I write all zeros? What is the true meaning of this one? This is called true exponent. So what is a true exponent if I write all zeros? Then that is 0 minus 127, correct? It is like you are representing minus 127, but we write zeros only, correct? Though you write all zeros, its actual value is minus 127, correct? So now easily you can understand that this pattern all zeros is representing very small number like 0, correct? That means when this is all zeros, then your real number is also near to 0, right? Very small. So near to 0. That means your circuitry design will be simpler to check whether a number is almost 0 or not. Okay, so example I will tell you. You have a number, you want to check. You asked your processor, my dear processor, I have a number, tell me that is 0 or not. Okay, then by checking this exponent, if all bits are zeros, then I can say that your number is almost 0, correct? So that's why example, you try to write all zeros. I mean, of course, and one more thing, in IEEE 754 standard, all zeros is not possible. Okay, so let me write example. Let's say 0 0 0 0, all zeros followed by 1 1. Okay, so what is going to be this value? This value will be mantissa. Let's take mantissa like this. 1 followed by all zeros. Then it would be minus 1 whole power sine. Sine is 0, positive, into 1 point mantissa. What is mantissa value? You know one thing. The weightage of this one is 1 by 2. 1 by 2 means 0 0.5. 0 0.5 into 1, 0.5. That means 1.5, right? 1 point, it's like this otherwise. 1 point m. M means 10000. 1.1000 in fractional representation is equivalent to a decimal value of 1.5. You know that, right? Into base power 2 to the power of exponent. Exponent here I am taking, so I am representing 1, but since it is excess 127, then that 1 is equivalent to 1 minus 127. That's why it will become 2 power minus 126. Okay, so it will be 1.5 into 2 power minus 126, right? So when this exponent is smaller, real your number also smaller, correct? So that's why by just seeing exponent, your so I can easily tell that my number is very small or not, right? So that's why, that's a logic. That's why we use excess 127 representation. It is naturally telling us that when the binary value is small, then this real floating point number what we have also small, correct? In that way, so it is going to tell us. But if you use 2's complement representation, then see, example, I want to write 0, otherwise I want to write minus 1, then I have to write all ones, correct? That is minus 1. So whenever I want to represent a small exponent, because when small exponent represents smaller number, correct, then for that we will be using all ones. But it's, if I represent it, of course it is actually in binary representations very big number, correct? So what I want to tell you here is, this pattern is not a regular binary pattern, correct? But if I use excess 127 representation, then all zeros, in naturally also all zeros, otherwise all zeros followed by 1, what is human tendency? Human beings are generally use this kind of 00001 for representing smaller numbers. But in our now overall floating point representation also, whenever your exponent is all zeros followed by 1, if you use excess 127 representation, then here we will be doing 1 minus 127, then minus 126, then you will get smallest number, right? So this is more natural way of understanding that your floating point number is smallest, right? Your binary pattern also supports it, correct? If I use 2's complement, then you will be writing all ones, but using that all ones, it will be little bit difficult for your circuit to check that it is smallest, right? For that, a different circuitry is required. Remember it, okay? So I will elaborate these details a little bit more after some point of time. At this moment, remember it. So we use XS127 representation. I will repeat it, whenever time permits. At this moment, I don't want to further discuss why XS127 generally we prefer over 2's complementation. Okay, but I gave you outline, right? If you don't understand, don't worry, because so the rule is important for us. That's it. The reasoning is at this moment is not required. But once you are comfortable with all these floating point numbers and their operations, then I will be teaching you why this XS127, why not 2's complement more clearly. Okay, for that you need some circuit design knowledge. I will be explaining you at end of the session. Second thing, why normalization? Sir, you said normalization. What does it mean, sir? So writing 1.m is called normalization. There are two things we can do. -1 whole power s into 0 point mantissa into base power exponent, okay, where exponent is of course e minus 127. Second thing, you can write -1 whole power s 1.m into base power e minus 127, right? Now the question, sir, while teaching decimal representations, that means when we were discussing about human being and their representations, then you use 0.m, correct? Still in our general conversation we use like this, we write 0.23 into 10 power 25, right, as a human being. But suddenly when it comes to computer, why we use 1.m? What's so special in 1.m? So sometimes we use -1 whole power s into 0.1m into base power e minus 127. So forget about this one, okay? This part we are focusing. Why 0.m? Why 1.m? Why 0.1m? So what is the difference between all of these? I am going to explain. First of all, let me ignore this point, okay? We'll come to that point later. At this moment, I don't want to discuss this, but it is also possible. According to standard, definitely we have to use, this one, 100%. We have to use only this pattern, no doubt. Don't forget about that. But for out of curiosity, you can ask me this question, sir, why not 0.m? I will tell you. For that, let me take one example. What is that example is, I am taking one binary pattern and I am going to ask you what is the value of that binary pattern if it is signed, if it is floating point representation, and that number I am going to give you is all ones here, 1 2 3 4 5 6 7 8, all ones followed by this is exponent, this is signed bit, this is signed bit, this is mantissa, like say 1 0 0 0 0, all zeros. What is the value of it? First of all, let me ask you. This is equivalent to -1 whole power 0 into, so we are just learning how to interpret this as a value, right? 2 to the power of, first of all mantissa, 0 point mantissa. What is the mantissa value? 5, we know, right? So whenever you have 1 0 0 0 so on, it is nothing but 0.5, correct? I am using 0.m representation into, if you have a doubt, you just check it out. 0 point mantissa. Mantissa is nothing but 1 0 0 0 0. So this is equivalent to 0.5 in decimal, right? Into base power 2 to the power of exponent. Exponent here is 2. See, all ones means 255, but from 255 we remove 127. Then it will represent 2 to the power of 128, correct? So it would become -1 whole power 0 into 0.5 into 2 to the power of 128. Okay, so what I want to tell you here is, of course it is nothing but 0.5 into 2 power 128. This number cannot have another representation. I will tell you the reason. We can write 0.5 into 2 power 128 as 0.25 into 2 into 2 power 128. So see, 0.25 into 2 into, this is 2 power 128. So 2 into 2 power 128 is 2 power 129. What I would like to tell you is, so this pattern is equivalent to 0.5 into 2 power 128. That can be written as 0.25 into 2 power 129. Then if this number also can be representable using another pattern, then I can say that one value has two representations. Slowly you will understand. So, but unfortunately, this number doesn't have another pattern. Why? 129 cannot be represented using our excess 127 representation. You see, the possibility is only minus 127 to 128. That's why I couldn't tell why there are not two representations for this pattern. But now I am going to give you another pattern which has, two representations. We will see. Example, let me take another pattern which is nothing but 1, 2, 3, 4, 5, 6, 7, 8. Okay. For this pattern, first of all, we'll see the value. For that value, there is another representation. Okay. I will explain that. Let us take this one now. So what is the value of this one? We are calculating value. So value minus 1 whole power S0 into base, sorry, mantissa 0.m. So 0.m means already this is we have seen. So which is nothing but 0.5, correct, into base power exponent. What is base here? 2 power exponent. Exponent is what here? I took one, this value is actually 254. Check it out. So 254 minus 127. Okay. So let me ask one question. What is the value of this one? It will be 0.5 into 2 to the power of what? 254 minus 127, 127. Remember it. Equation number 1. So this value can be represented using another pattern. Check it out. 0.5 can be written as 0.25 into 2. That is a trick. Into 2 power 127. Right? Same value. So 0.25 into 2 into 2 power 127 is 2 power 128. Now see, 128 is representable. 0.25 is representable. But 0.25 into 2 power 128 is nothing but this one. This one is nothing but this one. This one is already representable in using another pattern, correct? So to understand it, now first of all let me represent it. Let me represent this one, 0.25. So how to write 0.25? I think if I write 0 first, then 1 followed by all zeros, then that will become 0.25. If you have doubt, just check it out, because the weightage of this 0 bit is 1 by 2, this 1 bit is 1 by 4. So because of that, this is now fraction, right? So 0.5 into 0, 0, 0.25 into 1, 0.25. That's why this value becomes 0.25. Okay, mantissa 0.25. Now what about this one? Exponent is 254, right? But I would like to represent 255. We'll see. If I write ones here, okay? So 0 followed by all ones. I will tell you the reason for that. First of all, this is a different pattern than previous one. Previous pattern I am writing for reference. The previous pattern is 0 followed by 1, 2, 3, 4, 5, 6, 7, 0. Followed by, so here 1 followed by zeros. The value of this one you already remembered, it is this one, okay? Remember it. 0.5 into 2 power 127. Now, take the second pattern. I have intentionally created it and try to know the value of this one. Minus 1 whole power 0 into same and mantissa this time. Okay, so what's the mantissa of this one? 0. See, 0.m. M is 0, 1, 0, 0, so on into base. Base is what? 2 to the power of exponent. Exponent here, see the value 255 this time, correct? I changed the pattern, you should note down. So 255. 255 minus 127. If I simplify it, it would become, this is 0.25 if you check it out, because the weightages are 1 by 2, 1 by 4. So 0.25 into 2 power 255 minus 127, 128. So 0.25 into 2 power 128 can be written as 0.25 into 2 into 2 power 127. 0.25 into 2 is 0.5 into 2 power 127. So this representation is nothing but this one already, correct? So what I want to tell you is 0.5 into 2 power 127 has, these two are same, has two representations, this one and this one. So not only this, sometimes what happens for some number, you can have so many representations because of this, 0.m form. Now we will post-mortem it. We'll closely observe. So what is the reason you are getting multiple representations? One thing we should answer. Second thing, sir, why? What's the problem? When you have multiple representations, it will be difficult because you get ambiguity. Did you remember in signed magnitude representation and ones complement representation, we used to have two representations for 0, correct? When you have multiple representations for one number, then comparisons will become more ambiguous, correct? That's why it is better to have one representation for one number, correct? So that is what a simple design. We are violating the simple design technique, and that's why this will be a complicated thing. To avoid that, we have to normalize the mantissa. Second reason why we have to normalize the mantissa is, if you have multiple patterns, then we will be unnecessarily, wasting the patterns to represent a number, correct? If you had that patterns, that means if you had saved that patterns, then we would have used them for another numbers, isn't it? Then our representation capability will be increased by using same number of bits, correct? So when you have your representation capability increases, that means with same set of patterns, if you can represent more numbers, then definitely it would be better, isn't it? That's why, so we have to normalize the mantissa. That's why don't use 0.m format. We use 1.m rather than 0.m. So 1.m is going to avoid that problem. I will tell you the reason for that, okay?